Hello, we're going to begin the series of video lectures starting with Chapter 6. In Chapter 6, we're going to talk about normal probability distributions, and we'll start with what we call the standard normal distribution. The key concept of these standard normal distributions is that we're going to have a bell shape, right? That's the common normal distribution. And any type of distribution needs to have these parameters of mean and standard deviation. And the standard normal is very nice. It has a mean of 0 and a standard deviation equal to 1. Oftentimes, we simplify this by saying that the normal distribution has a mean of 0 and 1, right? Just like that. So this would be the standard normal with mean mu equals 0 and standard deviation sigma equals 1. And that would just be kind of what we would see, right? So again, a normal distribution, what makes this different than things we've covered before is we have a continuous random variable, right? One that whose outcomes are going to be somewhere on an interval. What is nice and what we want to keep in our heads about this is that everything we do, this graph is going to be symmetric. That everything that's true on the left side is going to be true on the right side of this. If that's the case, we say it has a normal distribution. Every type of distribution has a function. This is the function that normal distributions deal with. And it's a very complicated looking function. And to evaluate this, we're going to need calculus. The problem is we don't have that tool, and we must be able to find a way outside of that to determine the probability of these different events. That's what we'll talk about. The probability of certain events whose outcomes are on an interval where we would need calculus to compute it, but of course we don't have that. So let's look at the graph. A standard normal distribution will have the symmetric bell curve, where the area on the left and the area on the right are equal. What that means is the total area underneath, has to be equal to 1, right? Which makes the area all the way to the left and all the way to the right both equal to a half. And we'll use this information as we move forward. Before we talk about how we compute the probability given a normal distribution, let's first talk about an easier distribution, which is called the uniform distribution. The basic properties of a uniform distribution is that the area under the graph of this continuous probability distribution is equal to 1. And there is a correspondence between the area and the probability. So computing the area underneath this curve will be the same as finding the probability. And a uniform distribution has a curve that's a straight horizontal line. So the corresponding area will just be the height times the width of a rectangle. And if we can compute the area of this basic geometric shape, that will give us a direct link to the probability of a given event that can be modeled by this area. Right, so a continuous random variable has a uniform distribution if its values are spread evenly over a range, right? It's called uniform because the likelihood that any event or outcome will occur is equal between everything. The likelihood is uniform through all. And we get kind of a rectangular shape. That function that we can use is something we call a density curve. And what we're trying to do is, given a density curve, we want to be able to compute the probability or compute the area underneath said density curve. The total area has to be 1, right? The probability of all the outcomes added together have to be 1. And because the total area underneath the density curve is 1, That gives us this correspondence between the actual area and the probability. So now we can move on to looking at an example. So here we will walk through an example for a uniform distribution. Right? During a certain time periods at an airport, passengers arrive at a checkpoint, have waiting times that are uniformly distributed between 0 and 5 minutes, and we'll see this illustrated. Right? All of the outcomes are equally likely. So if I go from 0 to 5 minutes, I want to create a rectangle whose total area is 1. So if this base down here is 5, this height has to be 1/5, or 0.2. The waiting times can have any value between 0 and 5 minutes. So it's possible to have some obscure wait time with lots of decimals. Right? It would be really difficult to try and encapsulate that in terms of a certain number of outcomes, like 10 or 11 or 12 outcomes, which is why we use a continuous random variable to describe this. And by assigning this probability of 0.2 or 1/5, this assures us that the area underneath this rectangle, right, the shaded in region, is actually going to have an area of 1, which is what we want. And so now we can really answer any type of question we would have regarding this probability. So given a uniform distribution, find the probability that a randomly selected passenger has a wait time of at least 2 minutes. And so as we'll see in the pictures below, if I want at least 2 minutes, I want to look at my 2-minute mark and say, well, if I want at least 2 minutes, that's going to encapsulate all of the times I could be greater than that. But if I want to compute this area, this is just a smaller version of a rectangle. Its base, right, the area, is base times height. Its base is going to be 3 units. Its height is 0.2. And so as a final answer for an area, I'll get 0.6. But because we found a direct link between area and probability, the probability of this event is also going to be 0.6. Now we can move on to computing probabilities using a standard normal distribution. And again, a standard normal distribution is a normal distribution for a continuous random variable that has the parameters with a mean of 0 and a standard deviation equal to 1. For this to work, we want the total area under this density curve to be equal to 1. The way we're going to compute the probabilities, right, is we need to use technology, or in our case, we're going to use a table, right? If I look at this shape again, I should notice that this is not an easy geometric figure to compute the shape under, right? There's no good formulas from geometry. And so without the use of calculus, we're going to need some sort of computer-aided system or a table which represents the outcomes of these computer-aided systems. And we can look for an example of A2. This table A2 will be posted on Blackboard, and we can see basically it will look like this, right? It will have a bunch of probabilities, a bunch of z-scores, which we'll explain in a little bit. And so a few things we want to point out that for using this table, that this table is only designed to be used for the standard normal distribution. In later sections of this chapter, we will have various other types of normal distributions, which we will have to translate into the standard normal. This table A2 is on 2 pages. One page gives us values for the negative z-scores. The other page gives us positive z-scores. And maybe the most important is the table is the cumulative area to the left. Right? We'll talk more about that as we compute these different probabilities. When we work with this graph, we want to talk about these two terms of z-scores and area. And these z-scores are going to be the actual horizontal distance, which is the distance away from the mean. The area will be the region under the curve, starting at that vertical z-score and going all the way to the right. Z-scores, as we've said before, we want to try and round to 2 decimal places. And when we read these tables, we will use those 2 decimal places to determine the actual probability of specific events. One really common example is using bone density tests. Bone mineral density can be used to identify the likelihood of osteoporosis. And the results is normally a z-score. And we can use the standard normal distribution to really model these tests, to have a mean of 0 and a standard deviation of 1. So, a randomly selected adult undergoes a bone density test. We want to find the probability that this person has a bone density test score less than 1.27. And we can see from below that this is what we're going to do. The first thing we want to do is draw the graph, right? We want to draw the graph where we have the mean of 0, and we'll draw the curve. We want to plot our z-score somewhere on that number line. And this thing we have to shade in based on what this tells us. And because our score is less than 1.27, I will shade in all of the regions that represent an area less than 1.27. And we can see that this example has the answer for us right here. We can talk about how we compute that. Right? So again, we shade in this figure below. And so how do we read this score? Right? We need to find the area in the figure to the left of that z-score. And so what we're going to do is we're going to look at that table A2. When we look at this, we're going to look at the z-score of 1.27. The left columns here represent the ones place and the first decimal place. So we will zoom down all the way to the 1.2 spot. The columns are representative of the second decimal place. So if I want 1.27, I look at the 1.2 row and the 0.07 column. And I look at where they intersect. They intersect at 0.8980. That tells us again the area from the left to that z-score. That will give us not just the area from the left, but because we have this nice link between area and probability, it will give us the probability that a randomly selected person has a bone density score of less than 1.27. Let's look at another example. We want to use the same bone density test and find the probability that a randomly selected person has a result above -1. So if we follow those same procedures, what we'll end up doing is we'll draw a basic shape of this graph, right? It does not have to be exact. I want to plot that z-score of -1, which would be about there. And I'll put the horizontal line. And what we want to do is we want to shade in the region that this result talks about. And it says that the person has a result above this. That would be the area above this, which is this shaded region. So I want to find the area of this. However, our table tells us area to the left. So what do we do? Right? I want the area to the right, but our table only tells us area to the left. What we're going to do is use the fact that the total area is equal to 1. Right? That the area under all this curve is actually equal to 1. And what I can do is take this as my table value and find 1 minus the table value. If I do that, that will give me the remaining area to the right. And that's exactly what we're going to do. We look at this table, and we know that this table tells us the area to the left of that point. If we look -1 up in our table, we'll get that we have an area of 0.1587. And because the total area is 1, the area to the right, the one that we actually want this problem, must be 1 minus that, giving us an answer of 0.8413. The last standard type of example is trying to find the area between two values. And here it tells us that a bone density reading between -1 and -2.5 indicates some sort of issue. So we want to find the probability that a randomly selected person falls within a range. And so we'll compute this really the same way we did before. Right? We take our standard normal curve centered at 0, and I want to plot, in this case, the two different points, -1.00, -2.50. And if I want the area between them, it's really talking about a shaded region, right? That, some sort of smaller shaded region. And one way we can think about computing this is, well, if our table only tells us the area to the left, right? If I look up and find the area to the left of -1.0, I'll have overestimated my area. What I can do is find the value of -2.5 and subtract that value. So I can find the table value of -1.0 and subtract it from the table value of -2.50. And that should give me the area between the two curves. Right? The area to the left of the z-score of -1 is 0.1587, which we found from the previous example. If I look at the area to the left of -2.0, or I'm sorry, -2.50, I'll get 0.0068. And so the area between them should be their difference, which is going to be right there, -1.525. The generalized rule for finding the area between the two curves can really be thought of as this generalized area right here. And what we want to try and do is not try and memorize a rule or formula, but really try and understand what the graph is doing. And that we can consider the area between the two curves as B, our area we want to compute. And think about A as the area all the way to the left of the leftmost points. And then really simply thinking about B as really thinking about A plus B minus A. The area to the left of the right point. This is the area to the left of the left point. And doing more examples will help us understand and really try and understand this generalized rule. Because we're going to have these different types of notations, we want to be able to define them. So we'll define P of A less than Z less than B as the probability that falls between the z-scores of A and B. The probability that Z is greater than A is going to be the probability that Z is greater than A, and P of Z less than A, again, will denote the probability that Z is less than or equal to A. And we can use these to try and simplify the notation for what we've just talked about. The last type of problem we will want to know for basic, standard, normal random variables is going the opposite direction. If I know the area under the curve, can I find the z-score that generates that? And so what we're going to do is follow some repeatable steps that will sound familiar up to a point, right? The first thing we want to do is we want to draw a bell-shaped curve to try and identify the region under the curve. The problem is that region may not be a cumulative region from the left. And what we can do is try and use the symmetric nature of this and try and translate that into a known region that is cumulative from the left. And we'll talk about that as we get there. We're going to use table A2 to find the z-scores. And we want to find the closest probability for the body of the table. So let's look at how to do that. What we're actually being asked to compute is to find this idea of a critical value. And the critical value for a standard normal distribution is a z-score on the borderline separating things that are either significantly low or significantly high. And so in practice, finding the z-score from a known area is finding these ideas of a critical value. The way we notate that is by using the z with a little subscript of alpha. And actually what it means, z sub alpha, is the z-score with area alpha to its right. And the important thing is to remember that that alpha is the area to the right, but our table tells us areas to the left. So we'll use the symmetric nature of our curve to help find these solutions. So for example, let's find the value of z sub 0.025. What this tells us is I want my alpha, right, in the expression of z sub alpha to be 0.025. And based on this tells me that z of 0.025 is going to be the z-score with 0.025 as an area to the right. So what we're going to do is we're going to draw this. I have my standard normal curve, and I want a z-score. I don't know what that value is, but I know the area to the right needs to be 0.025. And what we've been saying is that this normal curve is completely symmetric. What that means, if I have a z-score here with an area to the left of 0.025, that there has to exist a z-score over here that's negative with an area to the left of 0.025. And this is what our table actually tells us. So what we can do is look at the table and try and find that z-score that's negative. And our solution will be its symmetric positive value. So let's look. Here's our table with the negative values, right? If we look up at the top, it shows us the areas to the left. And I want 0.025. I'm going to look for 0.025. So I'm looking, and I see 0.025 right there. What that tells me is I look at the row, that means the first two digits, the ones place and the tenths place is 0.9, and its column right here is 0.06. What that tells me is that this z-score here is going to be negative 1.96. And so its symmetric value over here must be positive 1.96. That will be our final answer. And as we can see here, that's exactly what we want to do. Now we want to have a word of caution, right? That when we find this value for z sub alpha, that alpha is the area to the right. So when we compute that, we can look at its symmetric nature. Another equivalent way to do that is to look at this. And it's to use the fact that the total area underneath the curve is 1. If I want to find a value, in this example, whose area to the right is 0.1, what I can do is think, well, if everything is 1, the area to the left of that has to be 1 minus 0.1, or 0.9. And look at my table for an area of 0.9. If we did that, when we look at the positive, I'd want something close to 0.90. And if I look right here, there is nothing of 0.90. I have things kind of halfway in between. So what we can do is, if no value really exists, right, no value is really going to exist, we can find the average of the points. So if I look at this first point here, that's going to correspond to 1.28. The next one corresponds to 1.29. I can divide that by 2. If I compute that, I get 1.285. That will be my answer over here, that this z sub alpha is 1.285. Again, I hope this was helpful, and I will speak to you next time.